Okay, welcome in. Let's dive right into this masterclass explainer where we're going to dissect Cambridge computer science exam questions with absolute undeniable surgical precision. Today we are donning our virtual scrubs, washing our hands, and stepping directly into the surgical theater. We're examining a topic that is quite literally the lifeblood of the Cambridge AS and A-Level 9618 computer science syllabus. I'm talking about output to console in pseudocode. Now listen, whether you are dealing with foundational syllabus codes like 0417, 0478, 0983, 0984, 2210, or you're tackling the beast that is 9618 today, the strategy is universal. If you want to achieve those top grade boundary-breaking marks, you need to treat these exam questions not as some frantic guessing game, but as a precise, methodical operation. I see two types of students all the time. Let's call them Alex and Sam. Alex overloads every single answer with raw computer science facts, totally ignoring the required analysis. It's just a data dump. And then you have Sam. Sam rushes the paper, panics at the sight of code, and completely misses the specific command word requirements. Both of these approaches result in a paper covered in red pen marks. Today, we change that. We are turning those red marks into green check marks.
So here is the absolute most crucial point you need to understand right out of the gate. Mastering console output in pseudocode is completely non-negotiable for your success. Why? Because it is tested without fail every single examination series. It does not matter what year it is, it does not matter what variant you are sitting, you will face this topic. You cannot hide from it. And honestly, once you truly understand the framework we are going to cover in this session, you won't want to hide from it. It becomes highly predictable. It transforms from this terrifying wall of text into a fantastic, reliable opportunity to secure consistent marks. Think of it as your anchor in the exam. When you open that paper and see a pseudocode trace or an output question, I want you to smile, knowing you have the exact blueprint to solve it.
Here is our playbook for today's session, structured exactly how the principal examiners evaluate your answers. We're taking you from core theory to fail-safe exam strategies. We'll hit theoretical foundations, then move into the procedural framework, dive deep into critical analysis, reveal the top examiner warnings, and wrap up with a final strategy that you can use tomorrow.
Let's start with Section 1, the foundational architecture. This is what proves to the examiner that you actually understand what your pseudocode is doing, rather than just blindly guessing.
You have to realize that examiners are explicitly targeting these three specific cognitive domains. They aren't just looking for a random output string, they are testing your underlying mental mechanics. It's not just about what you know, but how you systematically apply evidence-based reasoning. Let's break this down. The Cambridge assessment objectives require you to first demonstrate knowledge and understanding. This means knowing the definitions of variables, understanding loops, and recognizing the causal relationships in the code you're reading. This is where our student Alex usually stops, right? Just dumping knowledge. But you have to move to step 2, application. This tests your ability to take that core knowledge and actually use it in the specific unique scenario provided in the exam prompt. And finally, the holy grail, analysis. This demands that you break down the complex problem, evaluate its moving parts, and draw logical, undeniable conclusions about what will actually happen on that console. You need all three to get the marks.
Now, what's really interesting about this slide is that it reveals a massive secret pulled directly from the principal examiner reports. And before we continue, subscribe to our YouTube channel Ace the Exams at acetheexams_IGCS to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so back to the secret. Here it is. Pseudocode absolutely does not exist in a vacuum. Integrating it with other syllabus areas is exactly what unlocks those top-tier A-star grades. The highest-scoring candidates across the world don't just look at a pseudocode snippet in isolation. They connect it to overarching theoretical principles. They show a holistic understanding of the entire computer science landscape. If your given algorithm is outputting something to the console that is based on a database query, or maybe a specific complex data structure like a 2D array or a linked list, explicitly mentioning those cross-topic connections in your written explanation is what elevates a good, average answer into a phenomenal one.
All right, let's move to Section 2, the technical methodology. We're going to see exactly how this builds into the specific steps you need to follow when analyzing a complex problem.
Think of this as your internal mental engine. Before you even think about writing a single line of your answer on that exam paper, your data interpretation skills must flawlessly move through this specific three-part pipeline. It's like a built-in interactive workshop you do in your head. First, you extract.
For example, you might need to read and interpret raw binary representations or complex data tables right from the problem description. You are just gathering the raw materials. Next, you calculate. This is where you mentally or physically on scratch paper perform the operations dictated by the pseudocode, loops, and conditionals. Finally, you conclude. This means taking those computed values and forming an evidence-based interpretation of what the final string or integer output to the console will actually be. Our student Sam, the rusher, completely skips the calculate phase. Sam extracts the data, panics, and jumps straight to a guessed conclusion. And the examiners, they see right through it instantly.
And this slide brilliantly illustrates the standardized 5-step sequence that examiners desperately expect to see systematically processed in your working. It's a chain of logic. Step 1, identify the key elements of the code. Highlight the variables, the loops, the if statements. Step 2, apply the relevant computer science principles to those specific elements. Step 3, execute your analysis with crystal clear working. Don't do it all in your head. Step 4, verify your results. I want you to literally do a quick mental dry run. If you have a 60-second visual countdown timer in your head, spend 15 seconds of it just verifying. And step 5, present your final console output in the exact, specific format requested by the question prompt. If they want an integer, give an integer. If they want a string with spaces, include the spaces. Stick to this sequence and you build an absolutely unbreakable chain of logic that the examiner has to reward.
Moving on to Section 3, Critical Analysis and Evaluation. Beyond just writing the code or tracing it, top-scoring candidates secure maximum points by demonstrating high-level evaluative thinking. Now stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS, to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions.
Let's talk about the Find the Flaw challenge that so many students fail. Often, an exam question will ask you to compare 2 different pseudocode algorithms that produce similar console outputs. When asked for a comparative analysis, you must explicitly identify both the similarities and the differences. You cannot, I repeat, you cannot just list the features of algorithm A in one paragraph and then list the features of algorithm B in the next. That is a massive flaw that loses marks. Instead, you have to use comparative connectives. You need to use words like whereas, however, on the other hand, or in contrast. And are you making claims without evidence? Absolutely don't do that. Every single claim must be supported directly from the code snippets, actively justifying the trade-offs you've identified.
When evaluating algorithm quality and its eventual output to the console, examiners want you to dissect how these specific components affect the overall performance of your solution. Look at the slices here. Focus heavily on the big 3. First, time complexity. How long does it take the algorithm to loop through the data and generate the output? Is it a nested loop? That's going to cost time. Second, space complexity. How much memory is required during execution? Are you creating massive new arrays unnecessarily? And third, edge cases. What happens when the inputs are at their absolute extreme limits? Acknowledging the actual limitations of a piece of code based on these 3 specific areas is exactly what real evaluative thinking looks like to a Cambridge examiner.
Okay, Section 4. Let's look closely at the principal examiner reports to uncover the 3 biggest pitfalls that cost students easy marks.
The number 1 mistake, without a doubt, is vagueness. Examiners demand highly specific technical details rather than generalized assumptions. Remember Alex? Alex loves generalized assumptions. When describing what a line of pseudocode does, writing "it prints a number" is terribly vague. It gets 0 marks. Saying it outputs the concatenated integer value of the loop counter to the console is precise. It shows mastery. Specificity is absolutely your best friend in the surgical theater. Use the correct terminology every single time.
The second major error is completely forgetting to check your boundary conditions and edge cases when tracing your output. Students so often test a normal middle-of-the-road input during their trace table, but they completely forget to check what happens at the absolute limits. What happens if it's an empty string? What if the input is a 0 or a negative number or the absolute maximum size of an array? The pseudocode might output perfectly normal text 99% of the time, but if it crashes or outputs a bizarre error string on that 1% edge case and you miss it, you lose the evaluation marks.
And the third massive mistake is writing answers that are completely disconnected from the specific context provided in the question prompt. This is Sam's classic mistake, rushing past the introductory paragraph. If the question is specifically about a temperature sensor outputting warning messages to a console in a nuclear reactor, your explanation needs to reference temperature readings and reactor states. It cannot just talk about abstract variables like array index X and integer Y. Context is so heavily weighted in the marking scheme. You have to ground your code in the real-world scenario they gave you.
So I want you to burn this acronym directly into your brain right now. VEC, vagueness, edge cases, context. Use this memory hack to instantly recall these 3 examiner warnings before you even step foot into the exam hall. Ask yourself on every single question, am I being too vague? Have I tested the extreme edge cases? Am I tying my answer back to the actual context of the prompt? VEC, it's your shield against silly mistakes.
Let's wrap this explainer up by moving to Section 5, consolidating everything we've talked about into a practical, actionable application strategy for the 9618 paper.
Your ultimate goal is to showcase this complete life cycle on the page, from initial algorithm design all the way through to rigorous performance evaluation. Even when dealing with simple console output trace questions, examiners are constantly looking for underlying evidence of these practical programming skills. They want to see that you fundamentally understand how algorithms are designed, how the solutions are implemented via precise pseudocode, how they must be tested thoroughly, again, remember those VEC edge cases, and finally, how you evaluate their performance based on the time and space complexity we discussed earlier. It is a full circle.
Now, if you take away absolutely anything from this explainer today, let it be this: the method mark strategy. Listen to me carefully. Examiners will actually award you points for your procedural process even if your final console output is totally incorrect. Let's say you make a tiny, silly arithmetic error in step 2 of your trace table, but your logic for steps 3, 4, and 5 is absolutely flawless based on that initial mistake. If you have clearly written out your working, the examiner can follow your mental logic and award you vital method marks. They will carry your error forward and reward your correct logic. But if you just try to do it all in your head and just write down the wrong final output with no working whatsoever, you get a 0. It's that simple.
So I leave you with this ultimate fail-safe question to ask yourself on every single page of your exam. Did you explicitly document your systematic analysis? Did you show your working? Mastering pseudocode, console output, isn't just about getting the right answer. It's about proving step by painful step exactly how you got there. Students who implement these computer science strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCSE, to excel in your Cambridge examinations. Subscribe right now to at Ace the Exams IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for computer science and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here.